Alright, this video is to review one of the exercises, or actually one of the problems that we saw on a practice test for an IB exam, IB high level math. And what we have to do is somehow manage to show that the integral of this rational expression is equal to this rational expression, and we're supposed to use the substitution that x equals 2 times the tangent of u. And that certainly seems like left field because the answer has no trig in it and the question has no trig in it, even though square roots and trig are somewhat related, as we know. So the only thing you could do in a problem like this is just take the dive, do what it says, make x equal to 2 times the tangent of make x equal 2 times the tangent of u. So I do that, and naturally, because it's a substitution, I need to differentiate my substitution so that I can get dx in terms of du. So when I do that, the derivative of 2 tangent of x, or u rather, is 2 secant squared of u du, and so that means that this entire dx right here is equal to all of this stuff. So I have to replace this dx with all this junk right here. And x squared became 2 tangent of u squared, which is 4 tangent squared of u, and then 4 tangent squared of u again, plus 4. So we've got du now instead of dx, and all the x's have been replaced with their equivalent values that I established according to the given. Now, thankfully, I recognize some trig identities. The tangent of theta squared plus 1 is actually the secant squared of theta. So, oh, and by the way, I'm sorry, I factored out a 4 from both of these. That's why this became a 1. I factored out the 4, and then I took the square root of 4, which is 2. 2 times 4 is 8. So that's where that 8 comes from. And 2 over 8 is a quarter. So I extracted that. And then I remember my identity, which the tangent squared plus 1 is equal to the secant squared of an angle. And that's good news, because that enables me to take the square root of a perfect square. And I can divide common factors, and I'm left with this. Now, as it stands, I still haven't gotten something that's easy per se, but I think I have more of a sense of direction of how to differentiate or integrate this than I would the original expression. We're going to switch everything into sines and cosines so that I could see if there's anything that, rings a bell, so to speak. And when I do that, I end up with the sine squared over the cosine over the sine squared, and that is something that I can use u substitution for, because the cosine is the derivative of the sine. I can find a way to do some u sub. So u sub round 2. I use v this time. V is equal to the sine of u. I use a different letter because I can't use u sub already, obviously. So dv is equal to the cosine of u du. And so when I saw the cosine of u du up top, I replaced it with dv. When I see the sine squared, I replaced it with v squared, and that's easy to integrate. Now I put the sine back, so I switched back from v to u terms, and now I have to switch from sine terms into x terms. Problem is, my u substitution told me that x is equal to the 2 tangent of theta, and I have an expression, 2 tangent of u, and I have an expression with sines in it. That sucks. So I go over here and I say, well, look, if 2 tangent of u is equal to x, then the tangent of u is equal to x over 2. That's based off the given statement. All I did was divide both sides by 2, which means I can reference a triangle where x is the opposite of angle u, and 2 is the adjacent to angle u, side adjacent to angle u, and I can use the Pythagorean theorem then to find the length of the radius. Knowing the radius enables me then to calculate the sine. The sine of u is going to be x over the radius, or the hypotenuse, and since I use Pythagoras to find it, I can replace the sine of u with all this stuff. Now I'm starting to feel encouraged because I got a 4 and I've got a radical. Everything's starting to look like it did up top. And here I just multiply top and bottom by the radical, and I get exactly the expression I was looking for. So, thanks for watching.